Okay, cool. Hi all, this is gonna be the answer, or at least going through of APOW problem set 1. So, over here, we won't spend too much time on the non-calc since it's non-calc, so it's mostly general knowledge, but we will go through the pointers that is basically relevant in solving such problems. So let's get into it. So for question 1, the time taken for an compass set area with an increase in distance is basically equal. This is basically Kepler's law, because remember Kepler's second law? When you orbit, right? If you have the star here and then you have your satellite here, it doesn't matter where it is. If it's here or here, the area that it will encompass in a set amount of time, say t, is going to be the same because the speed here, so speed here is like faster, so it covers, like more distance as this. But the short distance from here makes up for it. Whereas for a point further off, even though it travels less during the same time t, because of its lower velocity, the fact that it's so far away just gives it more area. So the net outcome is that it's equal. Kepler's second law, basically. So I guess we'll just highlight it. Equal. And the key here is Kepler's second law. So for question 2, the coordinates of celestial bodies relative to Earth, so major factors. So major factors is of course going to be Earth's rotation. Because you're not observer on Earth, so the rotation would matter, because technically you're using like LAS, not like RA/dec. So yeah, Earth's rotation is definitely one, and also the motion of Earth around the Sun. Because when you think about it, right, it's like how when you're, in Singapore, in January you'll be able to see Orion, but you won't see it in like, say, June, because, of motion of Earth around the Sun. So, yeah. Actually, give me a moment. Is that why? Yeah, I think that's why. I'm pretty sure that's why you don't get to see Orion in like June, because of motion of Earth around the Sun. But anyway, so because 1 and 4 are correct, so the answer is 2, because they're the major factors. Actually, I will check this out. Is this why some constellations can only be seen in certain months? Probably. I will Google it after I'm done with the recording and then upload the clarification in the video description. So fret not, by the time you see this, if you have any questions, just check out the description. I'll probably leave all the relevant stuff here, so vid description, I guess. And then I'll highlight this, and this. So question 3, what's the approximate luminosity of a A-type main sequence star? This one's a bit of a guessing game, but I think, to be honest, when I did this, I wasn't too sure either. Just remember the general HR sequence. OBFG, KM, and then just remember that Sun is a G2V, and an A is like up here, so we can give a large estimate and just, basically we can eliminate these two immediately, and then we can just think and just go with D, because it's like an educated guess kind of thing. But if you really want to look at it, just check out the HR diagram. I think the HR diagram would be much clear-cut view of it. I should probably find a HR diagram next time, or include relevant diagrams. I will consider diagrams in further solutions, but for now let's just say that educated guess is the way to go. So D, because just recognize that Sun is G2V, and yeah. Anyway, so moving on, we have already settled the first few problems. So we move to the next page. So for question 4, if a star has a temperature of this much, the peak wavelength is, the answer is green. Simply put, Wien's displacement. So Wien's displacement law, the peak wavelength equivalent to constant over temperature, and we have temperature, we also have the constant, which is this. We do not question why I memorize constants. I just do. So this gives you, I forgot the exact answer, but it's approximately like the 517 nanometers. I think. IIRC. Regardless, it is in the green spectrum. And fun fact, some people might get confused because they think, oh, isn't the sun kind of here as well? Like, technically, yes, the sun's, I think it's like approximately this much, the sun's surface temperature. So technically, yes, the sun emits in the green, theoretically, if by surface temperature substitution. But because of the presence of, the continuum spectra, it's a continuous, and there's red and stuff, so they kind of merge all and just give you yellow. So yeah. I mean, I would honestly argue that atmosphere probably has some effects as well, but probably not that much because, when you have solar probes that are outside in space, they still see yellow. So, oh lol. But yeah, so for this one, it's just a simple substitution of 8, 9, 7. Okay, now I honestly just remember this, so I can't actually shorten it. It's not natural for me, unfortunate. So yeah, we take this, and then yeah, why did I actually delete it? I'm pretty sure it's 517, but just for BOD, I will approximate it, which is green. So yeah, Wien's displacement. Back then in APOW 1, I don't think we had really a strict classification for calc and non-calc, so that's why question 4 is a calc. But I think in upcoming APOWs, it's actually pretty much separate, so yeah. And this one's another general knowledge one, question 5. Not much to say about it. It is B. It is simply put just B. I'm not sure what else I can explain. And yeah. The rest of this is just, they're not exactly a method of detecting exoplanets per se, A, C, and D. Like, I mean, there are other methods such as gravitational microlensing, and then there's also direct imaging, which is also quite rare because it's got to be quite close. And then there's also transit, which is also quite common. I think there's one more, but I forgot. Unfortunate. So yeah, but yeah, there's definitely a few methods aside from radio velocity that you can use. Nice. Anyway, so following from that, question 6. Okay, one thing we need to know is that Singapore is 1 degree north, so technically we're like plus 1 degree. Okay, like approximately, basically, approximately. And the reason why I remember is because the MRT station 1 North. Yeah, 1 North. It's that simple. And also, fun fact, the reason why 1 North is the only MRT station without any capital letters is because it's technically like coordinates, so it's a fun fact, but irrelevant from Astro. But yes, it might help you remember the geography of Singapore. And another fun fact, our time zone is supposed to be like GMT +7, but we're actually +8 because, conventions and stuff. We used to follow Malaysia, I believe. So yeah, it's another fun fact. And that's also why our sun rises at like 6:30 a.m. when if you go to other countries, realize that their sun rises at like 5:30 a.m. So that's why, because we're not meant to be. So yes, it's fun fact, I guess. And it's also because we're like 1 degree north, which is why the correct answer here is actually B. Because it's too south. Unfortunate. Yes, we can actually see a star with this high declination, even though 89.5 is objectively, larger than 88.9. In fact, we can see theoretically, you can see Polaris. Like, really theoretically. But theoretically, it is above the horizon. So perhaps one day, like Singapore has a high enough mountain or something, you'll get to see Polaris. So yeah, this is possible. And unfortunately, you can't see the other one, so I'm sad. What happened here? Oh. 6 is fine. So yes, that is for question 6. And for question 7, this is another general knowledge. In fact, it's a cosmology question. Simply put, the answer is just, well, A. Because it's the chronology of the universe. It's not much to say. Okay, the way I remember is, right, just radiation started off at first because back then everything was too hot, so it's just all this radiation. And then stuff cooled down, so we had matter. And then now remember we have like expansion of the universe, right? That's caused by dark energy, so dark energy comes to us. That's how I remember it, basically. But yeah, this one's general knowledge, not much to say. This one, my interpretation is that the reason why C is an answer is because... Okay, so first, they ask you of a star that's the brightest. Basically, they're asking you for aperture, I believe. So, yeah. You just find the one with the biggest aperture, and then you realize that B and C actually have, like, the biggest aperture. I would assume that if it's a cluster, maybe magnification matters, so, like, the F ratio might sort of matter, but, like, if it's just a star, honestly, no matter how much you zoom in, it'll probably still look, like, the same, not gonna lie. And also, like, the reason why I think F doesn't matter is because over here, the F of this is not even stated, so I would assume it's not relevant, so we're just gonna look at aperture. So from sheer aperture alone, this one and this one has the most, or i.e. the same, 200 mm. But like when you look at it for a second, right, you realize that because of the nature of Newtonians or reflectors in general, you know, they have the secondary mirror design kind of thing, you know, right? So it reflects and stuff. So actually, refractors don't have that, right? It's just light coming in. They don't have this thing blocked, right? So technically, for the same aperture, a refractor would actually have a bit more light. So I give it C for this reason. It's a weird question, in my opinion. But yeah. Anyway, moving on from this page, we have question 9. And in fact, this is the last page. It's quite a quick go through, to be honest. Possibly because I did this earlier, so I kind of know how to do everything. But like, yeah, it's not easy. But if you know the right concepts, it's not hard either. This one's not a general knowledge question. To be honest, I got this wrong the first try. I thought it was D because Andromeda is huge. Andromeda has something on the scale of this. In fact, I think it's 160 the earlier. I forgot the exact number. I might correct myself later. You know what? One more thing to add to the description. What is Andromeda's radius? But well, Milky Way's one is closer to this. And I searched Triangulum, which is even smaller, so I think C is a reasonable estimate. This is just general knowledge. There's honestly no other way you're gonna know it. So yeah, we'll just go with C, but honestly we can give some BOD. If I was the setter, I think I'll put like 6,000 is a better estimate. But yeah, I can see why it's C. So yeah. Check M31 radius vid disk, note to self. And the short answer question, estimation question, not much to say, that the answers are all here. I'll be going through how we get the answers though. This one's just, you do math, there's not much I can say. The hard part of estimation question is on the spot estimating. Because most people do not really know what is, you know, going on with Arcturus. We just know it's like, I think it's a supergiant, I believe. I remember Arcturus and Tyrese. One of them is a supergiant and one of them's a red giant. I will also clarify this in the description. Which is which? Is Arcturus or Antares? Which one's a super giant and which one is not? I'll clarify it. But basically estimation rounds is just trying to figure out just what's going on, which is a bit difficult. So here's the answer. If you do some math, you won't find it. Like, let's just take a soccer ball to probably have like, is it fair to say like a soccer ball has probably like, I actually in fact did not do this question, so actually give me a moment and attempt this question. how long is a soccer ball? Soccer ball diameter? Oh, there's actually different sizes. 22. Oh, wow, okay. How about volume? Okay. Apparently it's like 22, 23. Can we just estimate it to be like 25 centimeters? And then Arcturus star. And okay, actually wait, I think we can get. Okay, Arcturus is a red giant. So Antares is the supergiant? Is it? Yes, Antares is the supergiant. Antares is the super. Arcturus is the giant. Okay. Regardless, let's go back to Arcturus. What is the radius of Arcturus? Let's take a look-see. So, radius of like, oh, it's like 28 plus 3.4, like 28 solar radii. And then the soccer ball is like, how much? Diameter of like 22, 23, 24, let's count 22, so it's like a radius of 12 cm. The radius of the sun. I vaguely recall it's like 6 something, is it? 696? Question mark? Oh, that's like, okay. 695 700 question mark kilometers. Is this correct? Yeah, it should be about right. So 12 cm versus this much km. Let's just say it doesn't look too good for the soccer ball. So if we plug this into the most scientific, because I'm using my phone, we will be able to obtain very huge numbers. Because if we just, you can divide the 4 over 3 pi constant out. The only thing that matters is the radius cubed, which is honestly a lot. So we have like 695,700, but that's in kilometers, so we add like 3 more zeros. But then we're using cm down there, so we need to add like 2 more zeros, I think. Yeah. And then we cube this. So we take this, divide by like 12 cubed. Yeah. Just say it's like huge. Okay, the answer I got is like 10 to the power of like 29. I'm not sure what's wrong. Well, let's see. Maybe they took it as like 70. Oh wait, no, they didn't. Hey, that's weird. Okay, I'm assuming they took a different soccer ball diameter? Maybe they... Oh wait, I am stupid. I forgot, there's a 28 that I need to account for. Haha, joke's on me. Give me a second. Okay. So over here we have this thing, and then we have this thing. Wait, I need to put the bracket here. Okay, awesome. Oh yeah, now we're on to something. Yes. After factoring in the 28 solar radii, I do in fact come across with 10 to the power of 33, which is the same order of magnitude. Mine's a bit different, it's like 4.46, but basically the same order of magnitude is correct, so yes. So yeah, few things. Arcturus is a giant, and Antares is a supergiant. Boötes, Scorpius. And then this one, we just take 28 multiplied by like 695,700,000 cubed over like 12 cubed. Get this kind of good enough. So yeah. And then this one is basically vis viva. So okay, the way to spot vis viva is basically, okay, you see here, right? They give you the orbital speed, right? And then they also ask you for the semi-major axis, and then that's kind of it, honestly. And just to give you this. So why is it important? Because we need to recognize that when we are looking at the vis viva equation, you're basically looking at this. Correct? Wait, the A looks a bit off. So why does it matter? Because you know the speed difference, right? So you can basically calculate v furthest and like v closest up, right? And you can also express it in terms of A, right? Because we have the eccentricity, which is gonna make life very easy. And why is that so? We will get to it in a bit, but first let me do some quick math. Or not even math, it's just writing. So what does this mean? Okay, normally when if it's eccentricity, I try to find a way to just imagine everything over like 100 per se. So you know, in this case of eccentricity of 0.75, we need to remember that the formula for eccentricity is basically just like, you know, yeah, wait, yes. So you have the far one minus, you know, the one that would be, yeah, away minus p over like a plus p, I believe. I do believe this is the formula. Yes. So so this one just, you know, away the apheapsis, this one's the periapsis, which I can't spell. So I'm not gonna spell them. But so if you think about this, right, you can, I like to equate everything to be over 100 to make life easier. So basically what you can do here is you can just do some, you know, nice subbing. So you can just take 87.5 minus this, right? And then you get, you know, 87.5 plus, you know, 12.5, which gives you nicely, right? So, and then because, you know, keep in mind that this gives you the major axis, but we're asking to find the semi-major axis, which is also what we sub in here. So the semi-major axis, what is it? It's actually, well, okay, remember this is unitless, right? But like when we want to convert it over here, we need to add like quote-unquote units, which is honestly in the form of A. So okay, basically the key thing is just the furthest distance, right? Far is equivalent to correct? And then close is equivalent to this. Because like, you know, because farthest must be away, right? Because we have eccentricity, which is not 0, which means that we're looking at something like this out of focus, which is empty. So when you're further away, it has to be over the, can I change the color? Yeah. So this is the semi-major axis, right? So when you're further away, that has to be greater than the whatever you're working with previously, right? So this makes a lot of sense. And on the converse, this also makes a lot of sense because this is definitely, you know, much less than, you know, A. So yeah, so we can basically re-express R in terms of A, which is going to be very useful. And why is it very useful? I'm running out of space. Give me a second, let me see how do I want to do this. Okay, I think I can just basically erase everything on top. Because it should be self-explanatory enough. Also don't mind the color change, I didn't really know what color I was looking at previously, but should not be a big deal. So yeah, so basically what we can do is we can just substitute it in, right? Because remember there's a 2 here, we can't neglect the 2. Basically what happens when you do a substitution is that you just get this. So you get like 100 over, so you know at first A is on top, right? So because it's actually below here, so A goes below. And similarly, this A7.5 goes below. Right? So this minus 1 over A. And similarly, this one is going to be 112.5 A minus 1 over A. And then now I'm just going to remove this. Oh crap. And then I will replace that here. So we will have 100 over 12.5a. Yes. And then over here, we will have 100 over 87.5a, right? So when we take out everything here and then we do some simplification, what you're gonna get is, wait, let me see, how do I write it down in like one line? Oh, because remember, right, the difference in the speed is 18 kilometers per second, right? So what does it mean? It means that, and then remember, when you're closer, you're faster. So what does it mean? Is that VC minus VF is equivalent to this in meters lah. So when we want to find that, we can basically write this as, and remember they both have this, right? So we can effectively take out the square root GM out. So what does this mean? This means that we can, so when we, you know what, I'm gonna explain this first and then I'll take it out so that it's easier for you to understand, because I am a bit running out of space. But basically, right, so because they both have square root GM, we can take square root GM out, right? And then we can just basically move it down here to make life easier, like down here. So if I re-express this, what does it mean? This means that 100 12.5a minus 1 over a minus another square root 100 over a7.5a minus 1 over a will give you 18000 over square root GM. Don't forget the square root, because you're actually taking like GM out from the square root, so you need to keep that. So yeah, we can express that as this. And then that also means we get to delete this finally, so we have some space down here, right? So, oh, this is not clean. That's, I need to stop selecting the wrong thing. So if we take this equation here, we want to like combine this into one, correct? So what we're going to do is that we're just going to multiply each side by 2.5 and 87.5 respectively. So what does it mean? I'm going to like write this down like in like one line because I want to make my life easier. But what does it mean? Basically means that, see over here you have 12.5, so you can take this minus 12.5, right? Get 12.5a, right? So you can take this and then 100 minus 7.5, and you have 87.5a down here, right? And all this is equivalent to this, right? So now we remove this so that I can write it back up here again, and which is basically just saying that 7.5 over 12.5a minus 12.5 over a 7.5a is equivalent to 18000 over square root GM. And then you need to make this observation. But what is this observation? In this case, well, it's the observation that actually 12.5 multiplied by 7 is 87.5. And what does this mean? This means a lot of things actually, because this means I can express it as this. Square root 7, right? Multiplied by 87.5. Wait, this looks kind of messy. Let me rewrite this. Because I was thinking about how I wanted to format it, so it ended up looking a bit messy. Well, I actually don't know why I just split into two. But I guess it doesn't really matter since I need to move it all over anyway, because I need to take out the a, right? So yeah, close to 12.5 over 87.5a, right? So this is equivalent to 18000 square GM once again, right? So now we can, take out the a. How are we gonna do that? I realized I did something wrong. Yeah, because we added this by 7 already, right? So this is actually 7.8 now, right? So actually, this can be combined. Right? To give you like that. So this is equivalent to, well, this, you know. And then we can basically just do some rearranging. So what we'll do, we will move this. Wait, actually, let me re-express this like this. And then we have like scurvy. Just want to replace it with like a dot. Oh wait, no, there's already a decimal point. Yeah, whatever, good enough. Actually, no, I'm having a bit of a pet peeve over here. Don't mind me. God. Okay, yes, like this. So what we can basically do is just we do some solving, right? So we move this one to the top. We exchange, right? And then we also move this one up. Okay, so it looks a bit messy, so it's okay. We'll write it out for you, alright? So what we basically get is that square root A is going to be equivalent to all this over and also square root 87.5, I believe. Yes, should be correct. So all we need to do now is just need to square everything, right? So I need to remove this. So all I need to do here is that I just need to solve for A, which in this case would just be the square of this really big thing here. For convenience sake, we can also just take GM out. So just take GM out. All this over which when you plug it in, solving, remember it's the sun, not Earth. So when you plug it in, you will get this. I'm not gonna plug it in now because once again, the best calculator I have at hand right now is Decimal Scientific, which is honestly not that bad at all, but it's on phone, so it takes very long for me to type. Just believe me, okay? Just remember some constant. I can give you the constants now, in fact. So just plug in G equals to 6.67 if you really want to be specific and add forgery. M should be equivalent. So you just plug in these two values and then you should get this. Yep. So yeah, the key concept here, I'm gonna leave it for a while so that you can take a screenshot or something. You know what it's called. Haha. But yeah, this wait, actually, I'm gonna be a nice person. I'm gonna put it back. I realize I have some space here. But it will be gone later anyway because I'm running out of space, like here for question 12. Alternatively, I can move this. Wait, I can't do this. I can move this mental note like here, and then I will see if I can fit this here, which I should be able to fit. So yeah, I don't really like question 12. I mean I like it, I guess, but I don't like it because like which genus that combine both absolute magnitude and apparent magnitude? That is disgusting. But yeah, so we cope basically. So right, first things you need to know, the log scale, right? So for each or the magnitude scale rather. So example, you have a magnitude of 1, right, and you have star magnitude 2. So how much brighter is the magnitude 1 star by magnitude 2 star? It's actually bright by a factor of, guess what? It's really weird. I do not know who asked, but it's brighter than this much. So for magnitude 3 star compared to 1 star, it's gonna be wait, this looks wrong. Actually, yeah. So 3 to 1 is gonna be like, yeah. This might be a bit clearer. Yeah, it's kind of curves basically. So why does it matter? It matters because we're gonna use it, obviously. And also remember they want it in solar luminosities, right? So once again, I'm not gonna give you like the direct solving. It's just if you plug in, you'll get the answer. But yeah, the way to approach it is cause right now we know it's already given absolute magnitude 2. So what does it mean? Absolute magnitude 2. So how much brighter are you compared to the sun? You are about to the power of 4.75 minus 2, much brighter than the sun. And because there's 60 of them, so then just multiply this by 60 times, right? Because they're asking for like the combined luminosity, correct? So you don't just basically add. And then this 5 stars of paramagnitude 3 is the annoying one, because I gotta solve it using the distance modulus, which is disgusting. I mean, okay, I guess. What can I say? Cry. So we just sub. They give you a paramagnitude, which is 3. Oh, another disgusting thing is that these in parsecs, but they give you in light years. So do some quick conversion. I think it's 3 or 4 or something, I think, but I really don't care. I think it's 4. I mean, I know the exact value of a parsec, which is like, but like, I'm not converting that from like light years, so never mind. We will just go with the typical 3.26 and call it a day. It's accurate enough. Okay, so we have the minus 3 here, and then move it over. So plus 3 here. So we get like 8. So it's like 8 minus 5. I'm really praying that I got the sequence correct. That it's like n minus m equals to like 5 minus 5 log d, not like some other way around, which is gonna make me really be stupid. But I will pray, okay? Oh wait. Guess what? I might be stupid. Give me a second. This is not very nice. I don't like getting this wrong, because that means that whatever you're doing here is gonna be wrong too. Give me a fat minute. Yeah. Wait, I'm correct. Yeah. Because if m minus m equals to 5 log d minus 5, then m minus m equals to 5 minus 5 log d. Okay. That is very nice indeed. Okay, good to know that I got my formula right. Okay, we move on. So basically you get 8 minus 5 log whatever this is, and then you just do the math. I think it's approximately some negative 0.98 something. I really don't remember. But you should get a negative number, which is less than? Yeah, less than negative 1. Yes, it's about like 2.9, I think. So if you get that, you're basically on the right track. And then so what you need to do now is you just need to do the same thing. So remember, you have this thing on top, right? And then you take this plus the same thing again, obviously. So you have this, right? And then you have 4.75. But remember, it's a negative number, right? Before it was a positive, it's minus, but then because it's negative now, it's reasonable to plus, right? So now you're actually plussing like 0.98, and then you're taking this times 5. So you add them all together, you get, I think it's approximately 169x. I forgot what x is, but yeah, you run it off, you get 1700, no problem. So yes, this one's basically the use of magnitude. You just use magnitude a lot, but just magnitude moduli, I guess. The classic distance one, and you also have the integrated one. So yeah, not much to say about that. Maybe I should rewrite this here. Yeah, I think I'll rewrite it here. Then you can have like a full picture of it all, I suppose. So we have 4.75 minus 2, right? This minus looks like a dot. That's not very nice. Multiply by 60, and then you add square root 5, 100, bracket this, and then if you ask me where this 2.88 came from, you get it from okay, done. Beautiful. Question 12. This is all the way up here. Yes. So this is all the answers for APOW 1. I hope after this one you have a better understanding of exactly what is going on with the answers and what mistakes you might have made and how you might avoid making them in the future. So yes, and as for the stuff I said I'll upload in the video description, yes, you can check it out. It will be there by the time I have it uploaded, so hopefully by the end of next week I would have able to upload it as well, so wish me luck, I guess. And once again, thanks for listening, so goodbye.